Good afternoon, everyone, and a warm welcome. On behalf of Nehru Planetarium, Prime Minister's Museum and Library Society, I welcome you all for yet another online webinar. Thank you once again for joining. On January 1st, 2024, the year started with XPoSat by our Indian Space Research Organization, ISRO's, making it the world's second X-ray polarimetry session after NASA. This X-ray mission will revolutionize the field by adding a complementary energy band. In the talk today, we'll delve into how the recent advancement in X-ray polarimetry and multi-band observations provide a unique opportunity to untangle the geometry of the region of intense gravitational influence. And to talk more on this topic, we have with us Dr. Aruberi. Planetarium, welcome you, ma'am. Dr. Aruberi is welcome. Dr. Aruberi is working as a DST Inspire faculty at IISER Mohali. Before joining ICR, she went to Royal Society Newton International Fellow at University of Southampton, UK. She is an X-ray astronomer by training, and her research interest includes study of neutron star and black holes. She is actively involved in carrying out multi-wavelength camping for these objects. This is especially a proud and a privileged moment for all of us that Dr. Aruberi was a part of X-ray astronomy led by Professor Biswajit Paul, PI of POLIX, onboard XPoSat, and who led the development of this instrument at Raman Research Institute. So today she'll be talking upon X-ray eye on the cosmic stage, unveiling secret of strong gravitational region with ISRO's XPoSat. On behalf of Planetarium, once again, ma'am, we welcome you
Thank
to
you.
speak on this such an interesting and recent development in space exploration.
Thank you. Thank you so much for nice introduction. Good evening, good afternoon, everyone, but good morning, so that everyone keeps awake during this talk, although it's afternoon time. So, as discussed, this talk will be focusing on a new mission which is launched by our own ISRO, XPoSat, and the title of my talk is X-ray Eyes on the Cosmic Stage, and Unveiling Secrets of Strong Gravity Regions with ISRO's XPoSat. So, as you all know, that XPoSat is a dedicated X-ray polarization mission, and this is India's first X-ray polarization mission. And considering the entire world, this is the second polarization mission in X-rays which is launched by ISRO. So it really marks the history in the X-ray astronomy field, and it is dedicated to study of strong gravity objects like compact objects which are known as black holes or neutron stars, which I will briefly discuss during my talk as well. So, beginning with the talk. So, as I mentioned, that it's like marking history in the field of X-ray astronomy. So, to begin with, what is X-ray astronomy? So, this is a branch of astronomy where we are dealing with space missions because X-rays cannot penetrate Earth's atmosphere because of absorption. So, different balloons, rockets, satellites are being launched. And if you look at the broad electromagnetic spectrum, which is shown here in the top left plot, so you can see the regions or the energies for which uh, X-rays belong to. And when we talk specifically in terms of astronomy, we astronomers basically discuss X-rays in terms of energies rather than frequency or wavelengths, unlike many other electromagnetic wavebands, for example, optical, or which is expressed specifically in frequency band, and we have radio, which again wavelengths, etc. We use these terminologies when we are expressing the energies or frequencies of those electromagnetic bands observations, while in X astronomy we are dealing it with photon energies, and roughly speaking we classify them as soft and hard X-rays. And by soft X-rays, we have all the energies which are less than 10 keV, and energies which are higher than 10 keV are classified as hard X-rays. So this is very loose classification, uh, which astronomers generally use for classifying this X-rays in terms of their photon energies. So, if we look at the history of X-ray astronomy, then there are different dimensions by which you can probe into the regions of strong gravity or looking at the celestial objects in the X-ray band. So since X-ray astronomy was began after just after the Second World War, we have several successful missions in terms of imaging, timing, and spectroscopy. So, to name some, so for example, in terms of X-ray spectroscopy, which is very useful information to get the flux as a function of your energy band. So to get those that information, we have current instruments like XMM Newton, which is doing really great in getting. So this is an example plot which is on the bottom uh, right, which is basically showing your flux, which is into units of count second per keV, and as a function of your energy. So you can see several spectral features and the shape of the spectrum, etc., getting data from these instruments. Then timing. We all know that India had a very successful multi-wavelength mission, which is known as AstroSat. And AstroSat has payloads on board, for example, LAX-PC counters, which is large area X-ray proportional counters. And this is another excellent mission for doing fast timing studies of these compact objects. Now, when I say past timing studies, it's basically to understand the dynamics around these compact or the strong field gravity objects, how the space time is changing over time. So, to get those insights, we need large time resolution or high time resolution, which is of the order of microseconds. And LAX-PC onboard AstroSat has that time resolution. Hence, we can probe into the strong field regions using those instruments. But we also have in the past several other successful timing missions, such as RXT, which was NASA mission. And again, in spectroscopy, also we had, several spectroscopy dedicated missions since 1995, which was ASCA. So there, after ASCA, there were several CCD based spectroscopy missions in our X-ray astronomy. And then for imaging also, we had several missions since its advent of X-ray astronomy. And the current instrument, which is Chandra, is really doing excellent job in getting the spatial information of these celestial objects, which are X-ray bright. But when we look at the top domain, which is polarization, there have been very few successful attempts in terms of probing the uh, strong gravity regions in terms of polarization or getting the measurements of degree of polarization or angle of polarization, which basically gives you another two degrees of freedom, which basically will allow you to probe into these strong regions and get further clearer insights. And I will explain you how polarization will help in the next slide. So to say what is exopolarization. So this is a short video which illustrates that how the polarized mirror or a source of polarized mirror can allow us to get better and clearer information, and why we say that this is emphasized that these are important for us to understand these strong gravity regions. So as you can see in this video, there's a torch with some unpolarized light, because when we say unpolarized, so light is or electric field are oscillating in all directions, and when it is passing through the mirror, which is acting as like a, you can consider it like a polarized glass, what you can also consider as sunglasses or something, and when it passes, unpolarized light passes through that, it becomes in one dimension. So this actually allows you to have a clearer signal which can infer, from which we can infer a lot of information we are looking or are after. So when I mention X-ray polarimetry techniques in X-ray astronomy, we do have, we have to rely upon different detection techniques, and when we are talking about different detection techniques, they are because of different energy. To work in different energy bands. For example, Bragg's reflection is a successful technique which can be used for constructing our detectors, but it is useful for energies which are less than 3 keV. And then we have photoelectron track, which is like another technique. I will be discussing photoelectron technique in a bit, and this will work will be a useful detection technique in 2 to 8 keV band. And then as we increase energies to the medium X-rays, then which is 5 to 30 keV, Thomson scattering is one of the prominent detection mechanism which can allow us to understand or infer the polarization measurements. And at very higher X-rays, we will rely upon Compton scattering as a dominant phenomena or mechanism on which your detectors should be built, which can allow you to get the X-ray polarization measurements. So now, based upon each of these technique, this particular slide emphasizes on different past, present, and future missions in X-ray polarization. So if you look at the top left plot, this is basically a detector which was used in OSO 8, which was the first X-ray polarization mission or rocket sounding rocket, which was using graphite, and it was working on Bragg's reflection technique. And then we all know that on board AstroSat, there was another payload which was known as cadmium zinc telluride detector, and that was working in 15 to 200 keV band. Although when this mission was launched, it was not primarily focused on doing X-ray polarization studies. But because of the unique capabilities of this instrument, CCTI actually allowed us to do X-ray polarization measurements, and specifically talking about sources like Crab pulsar. So it allowed us to do polarization measurements with a high significance. So in that way, it also marked the history in terms of X-ray polarization measurements for very bright sources with AstroSat CCTI. And since it works in a very higher energy band, we just realized that at very high energies, the Compton scattering is the main detection tool which can be used for X-ray polarization measurements. So this was the CCTI detectors were based upon this Compton scattering technique, and also this was one of the very important useful in terms of doing this X-ray polarization measurements. And then in 2021, that was the first dedicated X-ray satellite which was launched by NASA, and it works in 2 to 8 keV band, and that was using photoelectron polarimeter on board. And this was uh, the very first X-ray polarization mission or dedicated X-ray polarization mission, which was successful in gaining insights into the regions of these strong objects. And now, in on 1st January 2024, ISRO marks the history in launching a new mission, which is known as XPoSat, and which has an instrument on board called POLIX. This is a polarization instrument, polarimeter, and this works in the energy range of 8 to 30 keV. And this particular instrument allows us to detect polarization in the medium X-rays. And if you look at the energy range also, it's basically complementing your IXP, because IXP works in 2 to 8 keV band while POLIX works into 8 to 30 keV band. So having a joint observation of a single object in these two energy bands can be very useful for us to look at a broad X-ray polarization measurements. And then in the future, in also a very near future, I would say, we have another Chinese mission which is known as EXPE, and this will also have a payload which is PFA2 marked here, will be a polarimeter on board, and it will again work on photoelectron uh, detection techniques. So these are the few instruments which we have in our current X-ray world, or I would say, compared to many X-ray timing, X-ray imaging, X-ray spectroscopy missions, we still have very handful of missions which are available to us for probing the strong gravity regions and to understand better the effect of strong gravity in the presence of systems like objects like black holes and neutron stars. And it's very important to test general relativity and to get into more further insights about the geometry of these systems. It is important, and I think it will become more clearer as we discuss the science goals of this mission. So, imaging X-ray polarimeter mission, IXPE, again NASA mission. So, I mentioned that I'll be briefly discussing the detection mechanism in this particular satellite, which is NASA mission already launched in 2021. So, it is based upon this photoelectron detection technique. And what happens is the incident light, which is shown here in the basic right hand side plot here, it basically enters the detection detector, and there are gas pixel detectors on as a part of the detector, and the incident X-ray photon interacts with that gas pixel detectors, and basically they have track or form a track by their interaction with different pixels. And this the electron tracks which are formed after this interactions are way or the tool to measure the polarization in this in these systems or in these instruments. So this is what is in brief how the gas detection techniques work here, or the X-ray detection techniques work here in this space of gas pixel detectors. So it's basically electron tracks which are being used as a tool to measure the X-ray polarization. And this short video to just to give, because
The
it's
Indian Space Research
to give you some, I mean, because it was an exciting times for all of us to see this exhibition live, launch of this exhibition live. And this is a short video again by ISRO to see how the launch took place and how PSLV C-58 injected the XPoSat into its orbit.
The Indian Space Research Organization launched its first X-ray polarimeter satellite, or XPoSat, on January 1st, 2024, from the Satish Dhawan Space Center in Sriharikota. What is XPoSat and how is it a game changer for India? We explain. The PSLV C-58 rocket, with primary payload XPoSat and 10 other satellites, were deployed in circular low Earth orbit with an altitude of 650 kilometers and 6 degrees inclination. Built entirely by two Bengaluru-based institutes, ISRO's U.R. Rao Satellite Center and Raman Research Institute, XPoSat was conceptualized in 2008, and the formal pact with the space agency was inked in 2015. XPoSat is only the world's second such mission and India's third space-based observation after solar mission Aditya L1. XPoSat is to study X-ray polarization and cosmic sources, celestial bodies, including black holes, neutron stars, and magnetars. In 2021, NASA had launched Imaging X-ray Polarimetry Explorer to operate and perform X-ray polarization measurements within the soft X-ray band, whereas XPoSat will operate within the medium X-ray band. It carries two payloads, POLIX, that is polarimeter instrument in X-rays, and XPECT, that is X-ray spectroscopy and timing. According to ISRO, POLIX is expected to measure the polarization of X-rays in the energy band of 8 to 30 kiloelectron volts, emanating from about 50 bright astronomical sources of different categories, and XPECT will study the electromagnetic spectrum generated by different matter. X-ray polarization serves as a crucial diagnostic tool for examining the radiation mechanism and geometry of celestial sources. The insights derived from X-ray polarization measurements on celestial objects like black holes, neutron stars, and active galactic nuclei hold the potential to significantly improve the understanding of their physics. Across the world, there have been only a handful of experiments on X-ray polarization measurements. XPoSat is therefore expected to be a game changer in the field, as there have been only timing, spectroscopy, and imaging based studies done in this X ray frequency band globally.
So
The Indian Space
So I hope the video was clear, and it basically showed us the launch video and also introduced us to the instruments on board, namely POLIX and XPECT. So now I will be talking about instruments on board XPoSat. And so as was mentioned in the video, POLIX is the prime instrument which is responsible for X-ray polarization measurements, while XPEC is the X-ray spectrometer on board, which is shown here by arrows. So to begin with XPoSat, the first payload, which is POLIX, and our prime instrument for X-ray polarization measurements. So on the right hand side, we have a plot which basically is showing us the design of this POLIX. And what we have is on the top, which is a cylindrical shape structure, and this is basically a collimator. And what is the function of the collimator is to basically allow the incident X-rays to come or enter the detection system. And after that, below collimator, we have a scatterer. And as I mentioned, that this POLIX mission is based upon Thomson scattering as a detection technique. So the role of scatterer plays an important role here. It's very important in the sense because this will allow us to measure the angular distribution of the polarized X-ray emission. So on the left hand side, we see the incident photons which are falling onto this scatterer, and because of the this entire configuration will be rotating at a frequency of 2 rpm with respect to the observation axis. And this rotation will allow us to basically measure the angular distribution of the polarized emission. And this polarized emission, the angular dependence of this polarized emission is basically non-uniform. So you expect to see modulation in the distribution of your polarized emission, which will essentially give you the measurement of degree of polarization. And after that, scatterer scatters the incident X-ray photons. Those scattered photons basically enter the X-ray detectors, and those X-ray detectors are nothing but the proportional counters, which are gas proportional detectors, which again have gas, and with which the incident X-ray photons interact and generates the electron hole pairs. And these electrons will be recorded by the anode wires, which is basically shown here in the right plot. And this will be used as a tool to measure the degree of polarization or a detection technique. So to so this was a brief summary of how the XIM detection mechanism will work in Thomson's polarimeter, which is a basic working principle for POLIX. So this will be used to measure the degree of polarization. And if we look at the specifics of POLIX, so this is this photon collecting area of 640 centimeter square. So this is the photon collecting area of our detectors, which are configured on this detector. And it has a field of view of 3 degree by 3 degree, and this is the function of your collimator, which will help us in getting a field of view of 3 degree. And this will also another useful use of this collimator is also to reduce the background and restricting the field of view. So as I mentioned already, it works in the energy range of 8 to 30 keV, and it has proportional counters as a detectors on board. And now, since these X-rays are uh, can be absorbed if we use very high atomic mass material. So the scatterer material which is being used in this system or POLIX is beryllium, which has a low atomic number. And because of this, you can basically whatever incident X-rays fall onto the system will not be absorbed but will only be scattered, uh, and will allow the detection of the X-ray polarization. And the dimensions are given here: the mass of the payload, which is 125 kgs, and the data rate will be at around 6.5 GB. And it can have a modulation factor, which is basically what I mentioned was, like if it's a polarized X-rays falling, coming or incident on your detectors, it can detect the modulation factor of 40 to 44%. I mean, this is modulation factor which is being recorded here in the lab experiments. So another payload which is on board XPoSat is XPET, and this is a spectrometer. So now this is the same detector systems which were used in Chandrayaan 2, and it has been uh, getting data from Chandrayaan 2 and since 4 years. And it's the same CCDs which are known as swept charge detectors which are installed in Expect. And this is a very useful useful payload in addition to POLIX, because this can allow us to get long timing and spectroscopic information. Now, this polarization measurements is really photon hungry uh, thing, because it requires larger number of photons to be able to measure the degree of polarization, which means if you are staring at an object in the sky, you will have to look at it for weeks to months. And in that time scale, if we are looking at the same object with expect, we will be able to look at the variability of that system over this long time scales. And hence, if all the information for that long term period can be extracted, and we can get much better insights than what we have now. We do have several pointic observations as I discussed earlier, say RXT, XMM, which can allow you to do timing and spectral studies of these sources. But we have to keep in mind that we only have small amount of time which we look a particular source at. So which means that we do not have information, or we lack information what happened around that object or to the object after certain period of time. But by looking at a same object for weeks to months can really allow to do monitoring of that object. And since the time and spectral resolution is good enough to do optimum timing and spectral studies of the source, it makes use of all powerful tools installed in one system, which is XPoSat, and hence a very dedicated mission for studying X binary systems. And if we look at specifications of this particular instrument, expect, it works in the energy range of zero point 0.8 to 12 keV, and it has a energy resolution. So because if energy resolution plays an important role, because if you have to look at the spectral features such as iron line in the spectrum, I will be basically discussing how the shape of the X spectrum looks like and things like that. So spectral resolution here plays a role, that whether we will be able to resolve those features or not in the X spectrum. So it has a moderate spectral resolution, not bad enough, but just enough for us to resolve those sharp emission or absorption features which are superimposed or are on top of the X-ray continuum. And it has an effective area of 30 square centimeter at 6 keV. And even if the effective area is not large enough compared to many other available instruments, but since this instrument will be focusing or looking at a particular object for a very long period, so we can integrate lot of time to get enough signal to noise ratio. So in that way, it makes an excellent mission for us to look at strong gravity regions. And coming to the major science objectives with XPoSat. So I discussed about how the instrument will work and instrument configuration. And now we will be focusing on the science objectives which we are promised with XPoSat. So I will be discussing on the left hand side, we see a plot of an X binary system. So what are these systems? These are two star systems in which one of the object is a compact object, which is a black hole or a neutron star, which is sitting here at somewhere at the center. And then it has a companion star, which is a second star. And since neutron star and black holes have strong gravity, it basically accretes matter from your companion star and forms an ring like structure around the compact object, which is known as an accretion disk. And then we have strong jets which are coming, because in addition to the accretion or the inflow material, we also have outflows from these systems. And those outflows can be in a different bands, which is known as radio jets, because it is prominent in the radio band. And because of this accretion processes, we have lot of gravitation energy release, which is in the form of X-rays. Now with XPoSat, we will be after these objects to find out or probe regions which are closer to the black hole and the neutron stars. And second aspect would be to look at X-ray pulsars. And for X-ray pulsars, again, these are two-star systems in which you can see the matter is coming from a accretion disk here, and which is formed due to the inflow of matter from a companion star. And because these neutron stars, so now in this system in X-ray pulsars, we have the compact object which is a neutron star, and these neutron stars are specifically have a very strong magnetic field, and with the strong magnetic field, all the matter which is coming from the companion star will channel onto the poles of these neutron stars. And until today, what we believe is that we see X-ray pulsations because of the misalignment between the magnetic field axis and your rotation axis. And because of this misalignment, we tend to see X-ray pulsations. Now with XPoSat, we will be able to probe into magnetic configuration of these systems. We will be able to see at different rates of mass transfer how the geometry is evolving with time, and several other important aspects like how the X-ray polarization measurements are at different energies. And since it works in really broader compared to XPE mission, it will be helping us in getting out insights of X-ray polarization measurements in much broader energy range, and which is very useful, will be useful to probe energy dependence of X-ray polarization also. So I mentioned that I will be briefly talking about the X-ray spectrum and also the variability, which I very much discussed in the very first or second slide of this presentation. So on the left hand side, we have a typical X-ray spectrum, what we expect from these systems. So if you look at this particular plot, it's basically on the y-axis, it's giving you the flux information as a function of your X-ray energies. And if you look at this real data, which is shown here in this black data points, and we have different components or contributions from different regions of this X-ray binary system. So as I mentioned that it has an accretion disk, which is formed around the compact object, and then we also have a compact object. So we tend to observe at lower X-rays, we can see the thermal emission which is coming from the accretion disk or the some part of the accretion disk. And then we have hot electrons, and due to the presence of these hot electrons, which we can have Comptonized emission, which is something known as inverse Comptonization effect, and which basically contributes to the hard X-ray flux or the hard X-ray energies. So this is basically the mechanism by which your hot electrons is trying to give off their energy to the X-ray photons, which are soft X-ray photons working in the soft energy band. So the transfer of energies in the soft X-rays can, from these hot electrons, allows it to increase its energy. So hence becoming hard X-rays. So this is how it becomes a contribute to the hard X-ray flux, and this is known as Comptonized emission. And then we also have reflection of the disk, because from there is a direct emission coming from this hot electrons and things like that, but then this X-rays fall onto this accretion disk because they're coming from the strong gravity regions. So they fall at different regions of the accretion disk, and this is known as reflection. And then after getting bent towards this accretion disk, they come towards the observer. And this reflection component can be in the form of an iron line. If your accretion disk is rich in iron, it can lead to a emissions feature like an iron line, which can be observed in the X spectrum, or it can be a Compton hump, which is again the contribution of this Comptonized emission can be observed in this form of reflection feature in the X spectrum. So when I was talking about dedicated X spectral missions to probe into the spectral lines, and this is what I mean. So the iron line, for example, it's a spectral feature or an emission feature on top of this X-ray continuum, which is thermal emission and the Comptonized emission. To be able to look at or probe into the spectral features, we actually require strong spectroscopy missions as well. So that was the power of X spectroscopy missions. And then on the right hand side, we illustrate that how the how the dynamics around the strong gravity region objects evolve as a function of time. So you look at this each subplot in this big plot, it's basically a observation of the same source taken over several epochs or times. At each time the source was being observed, and this is a black hole source to mention, and every time we were staring at the black hole we see a different kind of variability patterns or the count rate patterns, and because the y-axis is your count rate and now this is a function of your time. So different patterns were observed as we observe the system at different time intervals. So basically again this illustrates that black holes are dynamic. The region or the space-time region or around these black holes change over time, which means we need to probe into these systems how the gravity works on these the atmosphere or regions around these black holes. With timing and spectral, we can do fairly enough to get the physical processes responsible for X-ray emission. And at different times, if we look at the variability light curves, we can look upon different frequencies which can be generated close to the black holes and then try to correlate with the X-ray spectral or physical processes. But then how the electric field oscillations are wiggling or dancing around these black holes, that information which can become get very clear insights about the accretion geometry was not able to infer, because these all current or rather previous X instruments were not allowing us to do polarization measurements. And then comes another important information which we can infer. So as I mentioned that the X-ray or the accretion geometry around these black holes change over time, which was evident from the X-ray light curves. Light curves is nothing but the intensity versus time plots, which was shown here. So if the variability patterns are changing, means something is going or changing in the accretion or the mass transfer that is causing changes around the black hole. So just to illustrate one, like for example, if this is a black hole and this is an accretion disk which is formed around the black hole because of the matter accretion, and then we have hot electrons which is known as corona here, and at a certain mass accretion rate we have a corona which is extended above the black hole, and that is also having some form of outflow in the form of jet. So this is one geometry which is observed at say time t1. And then if we look at the same source at time t2, we have another we have the same black hole, we are staring at the same black hole, we have the accretion disk, but now we see the corona has come closer to the black hole, and there is some evolution even in the form of outflows in the which is in the form of radio band. So which means that at two different times your geometry was different. It has changed from bigger corona to a smaller corona, and jet has changed from very large scale jet to maybe a jet which is a compact jet or something like that. So it has tend to show some changes in its accretion geometry, and now this is a function of your mass transfer from the companion star. And again, to give you how we infer the mass transfer change or the accretion rate changes, which I'm just talking about in for this plot. So on the right hand side plot, we have the intensity versus the time plot. And again, this is like a long term monitoring of a particular source. And this is observations taken by different all sky monitors like Maxi and BAT. These are available X-ray all sky monitors. Basically, they are scanning the entire sky to look at any new X-ray transient or any transients which is in the X-ray sky. So we see that for several days, because time axis here is in days, for several days there was no flux or X-ray flux measurements. It was zero, almost equivalent to zero. But at certain time there was a sharp rise in the X-ray counts, and as you can see, the X-ray counts have really increased. And this is in units of crab, because we believe that crab is a standard candle for X-ray observations in 2 to 20 kV band. And then this is basically normalized, so the flux is normalized with respect to the crab and they're the brightest. So we basically divide our count rates as with respect to the count rates observed in the crab observations. So this intensity basically gives you the evolution of your mass accretion rate, because intensity has come because of the gravitation energy release, and which is in the form of x-rays. So x-ray count rate increased as your mass accretion rate increased, and then it shows certain decay as well. So this is what is the changes in the mass accretion rate. And if you look at each of these data points with a pointed observation, say with XMM Newton, AstroSat, or any other available instrument, you will find something like this. So, which means that at each time interval, we have a different geometry which can be probed. But now, with having polarization and expect all together, we will be able to, with for polarization measurements, we require large integration time, because, as I mentioned, it's a photon hungry thing. And for having this timing and spectral studies, we have expect. And with this expect, we can, along with exopolarization, we will be able to have better insights into what is going on, how the shape of corona is changed over observations, and what is the role of magnetic field, or gravity, which and how it behaves or acts on this matter which is coming from the companion star and causing this x-rays. Another example, which is from the recent study with IXPE, to give you a better insights about what I'm trying to say. So with XPE, when XPE was launched, it observed a black hole binary system known as Cygnus X1. And for after the XPE observations, they were also coordinated with other multi-wavelength observations in optical and the radio bands. But when X-ray observations were done with XPE, and in this right-hand side plot, this orange or the yellow lines are basically giving you the direction of X-ray polarization, which were measured with XP. And then I mentioned that it's multi-wavelength observations were done, and these contours which are shown here are the radio observations which were taken for this particular source at a particular time. And when they put this X-ray and radio observation all together, they found that radio and X-ray polarizations are in the same direction as it is shown here. They are aligning to with each other. And when they were trying to understand or interpret these X-ray polarization observations, they came up. They looked upon different, the authors of this paper. They looked upon different plausible accretion geometries around this black hole. And there are several available or geometries in the literature that there can be a corona which can be uh, sitting at the spin axis of the black hole, and kind of close to the black hole, and also sitting along the spin axis of the black hole. Then there's something known as sandwich corona. They have spherical corona. So these are different shapes of corona and the accretion disk or the plausible geometries of the black hole, which are available to us to explain our X-ray observations. But in the past, there have been always confusion because of several degeneracies which exist in X-ray observations, and it was not clear that what is the correct accretion geometry or plausible or more plausible accretion geometry for a particular X-ray binary system. When they studied Cygnus X1 with XPE, they found that one can easily refute lamppost corona geometry, and in fact the observations kind of compelled them to believe in sandwich corona, which is here in the top right thing, which could be a more plausible geometry of a black around the black hole, which can be responsible for all the polarization measurements which were done, and they measured a degree of polarization of 4% or so. So, looking at X-ray polarization and the degree of polarization, they could really probe and accept or refute certain accretion geometries, which is a powerful tool in itself. Now, this XPE works only in 2 to 8 keV band, right? And with XPoSat, we will be having a broader energy coverage, which is 8 to 30 keV band. And when we talk about 2 to 8 keV band, this coronal geometry can be inferred. But then we also have something called as returning radiation. And returning radiation is nothing but, I explained that light is reflected off the accretion disk because of the strong gravity. So light is bent, it falls in one part of the accretion disk, and then it gets bent and then goes to the observer. Then basically this bending of light at different parts of the accretion disk is causing a scattering of the emission from the accretion disk. And this scattered emission from the accretion disk, when it is observed by the observer, it's highly polarized due to scattering. And this highly polarized emission predominates in the higher energy bands. So at higher energy bands, we can look upon this uh, or expect a higher degree of polarization at higher energies. So with XPoSat, we will be able to probe that energy domain in which the higher energy polarization measurements can be made, which is not possible with XPE. And then coming to the pulsars again, uh, so as I mentioned, in the case of pulsars, your matter is falling onto the poles of the neutron star, and it is misalignment between your magnetic field axis and your rotation axis, which is causing exapolarization, exapulsations. So now with XP again, they observed several dozens of exapulsars, and with exapolarization measurements for the first time allowed them to measure the misalignment or degree of misalignment, which is given here by the theta parameter, and this is of the order of 12 degree. And this is like a plausible accretion geometry around this exapulsar, which was proposed for a particular exapulsar they observed. So when they are able to look at exapolarization measurements, they can actually look at different parameters and put it in a equation and get different in I mean parameters which can infer you about the spin angular momentum, the orbital angular momentum of the system, the orbital angular momentum of the pulsar, and how much it is inclined with respect to the magnetic field, etc. So those things can be inferred only by exapolarization. It cannot be done otherwise. People can try to do theoretical modeling, but that is again having certain assumptions. But with observations, it will become a direct measure of your all these set of parameters. So in that way, it really is an important mission to understand how to infer a clear information about the accretion geometry, changes in the accretion geometry, or how the magnetic field has changed over time, or how the magnetic field configuration is around these strong gravity objects or strong magnetized objects if it's a neutron star. So another case of exapulsar to illustrate it better, when I say the changes in the accretion geometry as a function of time. So in the case of exapulsars, since the matter is accreted onto the poles of the neutron star, based upon the mass accretion rates, we can also have different uh, basically, this is like a matter which is channeling onto the poles of the neutron star, and at higher mass accretion rates, you basically see that this accretion column or the funnel which is formed onto the poles of the neutron star due to mass accretion is completely filled. And in that case, it has been proposed that it follows a certain geometry which is known as fan beam geometry. So the beaming pattern is of the fan beam, as named as fan beam. And if it is a low mass accretion rate, which is shown here in the again the left right hand side plot on the top, this is basically the pencil beam pattern, because at low mass accretion rate you still have some space available in this cylindrical funnel or the funnel which is formed onto the poles of the neutron star. And because of that empty spaces in between this funnel, you have x-rays which can penetrate from this funnel or accretion column and interact with different heights and depths, and you tend to observe the pulsation pattern in a with more modifications. While in the case of fan beam, the X-rays are basically penetrating close to the neutron star. So these are two different accretion geometries which are proposed for X-ray pulsars. And now for these systems, there have been predictions for different degrees of polarizations for different plausible geometries. So on the bottom panel, we have a plot from Mesuras in 1988. These are theoretical predictions at which says that for pencil beam and fan beam patterns, we will expect a different degree of polarization. And this degree of polarization, you can see, for example, in pencil beam, when you're it's highly pulsed fraction or highly pulsed flux available, like a peak of this profile, you see a dip in the degree of polarization, which means there's sort of an anti-correlation here. And compared to the fan beam, which is correlated to the flux. So degree of polarization, we expect to see different changes as the change in the accretion geometry. Now with XPoSat, another advantage, in addition to see the energy dependence of this X-ray polarization measurements, we can, since the energy band extends up to 50 keV, we have another important features in the X-ray pulsar spectrum, which is known as cyclotron lines. And these cyclotron lines are the direct evidence of the magnetic field of these neutron stars. And in the bottom panel, we basically shows the simulated spectrum for different instruments. And on the y-axis, it's like a flux in units of counts per second per centimeter square keV per keV. And then on the bottom panel, we have the energies of X-rays in kilo electron volts. And this is like simulated X-ray spectrum for different instruments which are available to us. And for example, I just pick up this AstroSat LAX PC, and now XPoSat POLIX works in up to 50 keV for very bright X-ray pulsars. And you see these dip-like features which are observed on top of X-ray continuum. And these dip-like features or absorption features observed in the X-ray spectrum are known as cyclotron lines, which is, if you want to understand what these cyclotron lines energies are, basically this is the electrons which are occupying certain levels in the presence of magnetic field, and when the X-ray photons interact with these electrons and the different energy levels which are known as Landau levels, this interaction causes this resonance scattering of the incident X-ray photons with scattering due to these electrons. And this resonance scattering is observed in the form of absorption features in the X-ray spectrum. And this, in majority of X-ray pulsars, we have found that the cyclotron line energies in the X-ray spectrum do fall between 30 to 50 keV. However, there are sources where we have cyclotron lines above these energies, and now this is a function of magnetic field also. So depending upon the strength of the magnetic field, we expect to observe the expected value of your cyclotron line energies. But if your source or a X-ray pulsar has a magnetic field which leads to the E cyclotron line energy between 30 to 50 keV, we can probe X-ray polarization at those energies. And from theoretical predictions, again by Mitsuzuras, it has been predicted that at those energies which are close to the cyclotron line energies, we tend to observe very high degree of X-ray polarization measurements, which means that if we are able to probe those energies or energy regions with X-ray polarization, we can basically kind of accept or refute those models. And in addition, we will be able to probe into the magnetic field configuration. By probing the magnetic field configuration, I mean, because when we are looking at the geometries of these systems, specifically X-ray pulsars, we have certain assumptions in their modeling. For example, we believe it's a dipolar magnetic field. Now, with dipolar magnetic field calculations, we expect a higher degree of polarization at cyclotron line energies. And if we do not observe those high degree of polarization at higher energies, which means that something is missing in the current model, and which means either we are missing the understanding of our current models, or it requires refining in the form of contribution from a higher orders of magnetic field. So which means having probe of this X-ray polarization can really give us better insights about the magnetic field configurations. And lastly, I would say with XPoSat, we really have high hopes in complementing it with IXPE and to get better and better insights into these objects in a broader energy band. And with all this, I will say thanks, and I'm happy to take questions.
Thank you so much, ma'am, for such a illustrative presentation. Also, give us a lot of insight related to the mission in detail, and also the basic physics and details about the entire XPoSat working. So,
Thank you.
as the year 2024 started with a lot of developments in terms of like XPoSat, or we can say the Aditya L1 reaching to the Lagrange 1 point. So, I
Yes,
think we have really, and even ISRO announced a lot of good projects in the
yes,
coming years. So, everyone is so excited, and our
yes,
heartiest congratulations to the ISRO and to the
yes,
people like you who are involved in this scientific temperaments and involving in a lot of developments that are taking place uh, in terms of space exploration programs. So I
yes.
think with this note, we are happy to take some questions. People who are with us watching live, I request if you have any doubt, any questions related to the presentation or related to the topic, please feel free to drop your question in the chat box. I can see many of the people are live, but if you have anything related to the topic, you feel free to post it.
Yeah.
So we have one
Thank you.
question.
Yeah.
Chinmay Shahi. Thank you, Chinmay. Glad to see you that you are here with us live. He's one of the students for Delhi College of Engineering and also
Mhm.
very actively involved in many of the programs organized by Planetarium.
Yeah.
So, in his question is the mission goal similar to the Chandra X-ray telescope?
So Chandra X-ray telescope was dedicated X-ray spectroscopy or imaging mission, while XPoSat is a dedicated mission for doing X-ray polarization measurements. So the detection technique itself is very different from what it was used in Chandra. So what exactly do you have any precise thing which you would like to ask in comparison to Chandra, or what exactly you would like to know?
Chinmay, we request if you can just post it little specific, like what exact comparison you were asking. So ma'am can then give you the better comparison. Meanwhile,
So
others
if
can also
so,
post. Yeah.
So if you're talking about the energy range, it is not working in the energy range which is of Chandra. So for example, Chandra is working for soft X-rays, which is like around zero point 0.1 to 10 kV, while POLIX, as you can see, it is working in 8 to 30 kV band, which is again almost medium X-rays. And then even if you compare it with XPEC, which is another payload on board, which is a timing and spectrometer, it works in like zero point 0.7 to 12 kV. And again, if you try to have one-to-one correspondence with Chandra of XPEC, which is a timing and spectral instrument on board, now XPEC has a moderate spectral resolution. So I would say it's not really beating the Chandra observations, because Chandra observation was the first dedicated mission for having high timing, high spectral and spatial resolution observations. While expect, which is onboard XPoSat, will not be able to give you that detailed insights about the spectral feature, but it is very useful to have fast timing information. Something similar you can consider it with LAX-PC, which is another timing instrument on board AstroSat. But this AstroSat LAX-PC works in 3 to 80 kV band and has much higher timing resolution compared to expect. So expect something lies between say Chandra and AstroSat LAX-PC. So this is what I can roughly give you a comparison of Chandra and uh, ExpoSat in general.
Yeah. So in continuation, I think he posted, I remember the Chandra image of Crab Nebula pulsar.
Mhm.
Can we study about this pulsar from expect as well?
Yes, so definitely we can study crab pulsar with XPoSat, and that is one of our main goal also to study. But as I mentioned, that Chandra was dedicated mission for high spectral and spatial resolution, has a those as a main strengths of that satellite. But expect or polix is not meant for spatial, they are not spatial instrument for meant for spatial resolution. So they are more of except polarization and timing and spectral study instruments. So that is a complementing information which we can get in addition to Chandra's observation, which can allow us to probe the spatial extent of that particular pulsar. So we will be able to probe crab, but we will be doing or probing different dimensions of crab with this instrument or this mission.
I think he got his clarity. Thank you.
Yeah.
Anyone else would like to comment? Would like to like ask anything, query related to the topic? You can post in the chat. We'll be taking those questions from there. So meanwhile, ma'am, everyone like maybe trying to pose their questions. I would like to personally ask, how was your experience working on the payload, one of the payload? Because just wanted to get the insight about it. How was the experience and all, and what understanding you got during this research?
So I would say, first of all, I didn't work on the instrumentation side for this payload. I'm a part of scientific science team
Yes.
of this XPoSat. So for instrument design and everything was carried out in Raman Research Institute, and of course, Professor Vishwajit is my thesis supervisor, and also a close collaborator with whom I'm working on different projects. So for I mean, getting the science, new science which we can obtain from this X-ray polarization instrument was itself a new excitement for us, and
Yes.
specifically for the Indian scientific community, because this is like a world's second X-ray instrument, and again working in a different energy band. And with XPE, actually, we got several observations which are not aligned with the current theoretical predictions, but we always have a say that okay, it may be a function of your energy range, maybe at this energies it may be not possible to prove that and this and that, but at higher energies it may be. But now with exosat we can give definite answer whether we can or we cannot accept a certain model. For example, if I discussed briefly about xa pulsars. So with xa pulsars, the theoretical predictions do say that we expect a very high degree of polarizations, up to 80% or so. And with XP measurements, we got sort of disappointed with XA pulsar observations because the polarization measurements was only 15 degree or even less in certain cases. Now, what is responsible for that lower degree of polarization is not very clear. So, the first question or the answer to that lower degree of polarization could be that it may be like 2 to 8 kV band, because these are hard X-ray pulsars. So, we expect a higher degree of polarization at higher energies. And the second could be, you can say, uh, it's basically it could be a different reason altogether that we are not able to probe at other higher energies with XPE. So that information is still contradicting with observation. So, and as I mentioned, the theoretical prediction. So it could be our hidden assumptions, because when we are doing theoretical modeling of these systems, we have certain assumptions. As I was discussing the dipolar magnetic field assumption also. So if those assumptions are true, then why we are getting lower degree of polarization? But now with 8 to 30 kV band coverage with XPoSat, we have a new hope to look at a different energy band and see if we still get a same degree of polarization or we expect a higher degree of polarization. So in that case, it will be really useful for or
Yes.
helpful in answering several hidden or mysteries right now for us. So
Definitely.
yes, it was a real excitement for scientific community.
Definitely, definitely, and all such missions are involving a lot of research organizations like
Yeah,
IUCA, ISR,
yeah,
Aries, Nainital. So it's really a kind of a great boom
yeah.
for all the scientific community, ma'am.
Yes, yes, definitely. And definitely based upon the science demands, ISRO basically asks us always in every meeting that what is the scientific community wants next for us to look at or probe or develop. So I think given new science which will come out from XPoSat, we will have several future exopolarization missions also.
Definitely,
So in that case,
definitely,
yeah, so there are several meetings before the launch of XPoSat organized by ISRO, where they required inputs from the scientific community that how the broad X-ray polarization measurements will be useful, and how what sort of things are in demand by the community. So this is what I think is a really nice.
definitely, and this will also help us in developing new ventures of research for
Yes,
students who wanted to join these fields. So
yes,
probably in
yes,
coming times, a lot of new developments will happen in
yes,
terms
yes.
of science and
Yeah.
technologies.
Yes, definitely. It will open up several opportunities for people who are, I mean, science enthusiasts, or if they are instrument enthusiasts. I think there will be
Yes,
several things which will go.
lot of things.
Yeah, exactly.
Yeah. So with this, we have another question, ma'am. He's Yash Rawat. What are some examples of multi-band observations?
Okay, so I may not have a plot, but let me try to figure out if I can show you some plot. Okay, this plot is fine. So if you look at this plot on the left hand side, this is the artist impression of an X-ray binary. Nothing to scale here. Please do not have a like. This is not a real scale, so it's just an artist impression. So as I mentioned, that their matter is accreted onto the system, and we have a compact object sitting here at the center. It forms an accretion disk, which is a angular disk or annular disk, which is around the black hole. And closer to the black hole, it is very hot and it emits in X-rays. But as we go to the outer rings or the outer disk, it has something called as X-ray reprocessing, which means X-ray has lost its energies and goes to a lower frequency or the lower energies. At lower frequencies, they can be predominant even at optical band. So outer part of the accretion disk, which is formed around the black hole, is in the form of optical emission, and that optical emission is now another waveband, right? It compose a different frequency band. And then I was discussing about the radio jets, and as the name suggests, these are in the radio band. These are certain outflows. So when matter is accreted onto the system, there are some mechanisms by which you can also observe certain outflows from these accreting systems. And these outflows are really beamed and relativistic jets which are coming out of these systems, and they are observed in the radio band. So if we are able to combine radio, optical, soft and hard X-rays, because hard X-rays, as I was discussing in the X-ray spectrum, can come from the hot electrons in the system, and combining all these energy bands or frequency bands, we compose the entire electromagnetic spectrum, which can be observed in this particular system. So this is one way. There is something called as accretion disk and jet coupling. And accretion disk jet coupling is nothing but the role of accretion disk and the formation of jets in this system. So if we are able to probe these systems simultaneously in all these wave bands which I am discussing, then it's become part of multi-wavelength studies. So is that clear?
I hope, Yash Rawat, your question, you are clear with your doubt. So I think with this, we'll wrap today's session. Else the video will become a little longer in terms of streaming. So if
Sure.
still you have any questions, feel free to write to Nehru Planetarium at gmail.com pertaining to the session. If something we could help you with this, we'll definitely would like to bring that bridge between Aru ma'am and you, and we'll love to share your questions with Aru ma'am so that she can answer. And
Sure.
again, once again, as the topic clearly suggests, that unveiling secret of strong gravity regions, we really hope that this mission of ISRO's XPoSat will definitely uh, unveiling secrets, will unveil the secrets, and we'll get a lot more insight related to that field. Uh,
Yes.
thank you, Aru ma'am, Dr. Aru, for
Thank
your
you.
time, and sharing such detailed insight related to the missions and the payloads. So we
Thank
really
you.
look forward to work again with you on some
Sure.
other topics related to the topics. Thank you
Sure.
once again. Thank you for all the participants for giving your time and coming here and to attend this live. So to take
Thank
care
you
of
so much.
yourself. Yeah. Thank you, ma'am. Thank you once
Thank
again.
you. Bye. Thanks for inviting.
Bye.
Bye. Thanks.
Thank you. Bye. Take care.